We are recording. Yes,
All right.
okay.
Verify that we see me here, maybe. Okay. So, talking about down here again, the geometry of time. And so, last we spoke, we were talking about possibilities of geometry of the universe if we have isotropy and if we have homogeneity, and that's that it could be either flat or spherical or hyperbolic, i.e. saddle shape, and we wrote down the possibilities for the metric in those cases, and so then finally we had that the metric on a two-sphere within, what do I want to say? Where do I want to start? I want to connect with where we were last time. Right, so I'm just going to rewrite kind of the last thing. I think I had said that similarly, a three-sphere consists of two spheres stacked along a perpendicular axis. I think that's where I was last time. Okay, so I'm just going to rewrite that part as a connection to where we were. Similarly, a three-sphere, which is what the universe would be if it's spherical, consists of two spheres, two-dimensional spheres, stacked along a perpendicular axis, but that axis has to be in a direction perpendicular to every direction in our space. And the radius of each two-sphere that we're stacking is r sine, I'm going to call this angle chi, or chi, really is probably the better pronunciation, but here in Marker we often say chi. R sine chi, which is r sine of little r over big R, where big R is the radius of the force of the three-sphere. The radius of the whole three-sphere. Metric on each two-sphere that we're stacking to make our three-sphere is r squared sine squared little r over big R times d theta squared sine squared theta d phi squared, where this piece right here is r squared sine squared chi, which is the radius of that two-sphere squared. And again, this is all analogous to constructing a two-sphere out of one spheres. What's a one sphere? What's another name for a one sphere, a one-dimensional sphere? Circle. Yeah, so remember that we had this picture of creating a two-sphere by stacking a bunch of one spheres. And so here is the radius of the two sphere, and here is one of those one spheres that we're stacking in order to make it, one of the circles that we're stacking in order to make it. And here is us at the origin. And we measure distance along the surface of the sphere because we live on the surface of the sphere. We're imagining ourselves to be two-dimensional creatures living on that surface. And so we measure radius little r for the circle. But if you will, the actual radius on some level is capital R sine theta, or in other words, capital R sine little r over big R. And if we are living on this sphere as two-dimensional creatures, we could figure out that we're actually living on a sphere and not on a plane by, in principle, you could measure out some circle of radius little r, measured along the surface, because that's all you can do is move along the surface. You could walk around that circle with your roller tape and measure its circumference, and the answer you get will be r sine little r over big R times 2 pi. Circumference of your one sphere circle of radius, if you will, little r is equal to 2 pi times r sine theta. So that's 2 pi sine of little r over big R. But what would our creatures, if they imagine themselves to be living in a flat universe, what would they expect the circumference of a circle of radius little r to be? Well, so if you think you're drawing a circle of radius little r on a plane, what do you expect the circumference of that circle to be?
2 pi r.
2 pi little r, right? This is as opposed to 2 pi little r. You're going to get something that is a bit smaller than that. You think the radius of the circle is little r. It's actually capital R sine little r over big R. It's actually this distance here, which is less than little r. Problem 3 on the homework asks you, okay, if you could measure distances to a precision of 1 meter on big circles that you drew, and if Earth was a cue ball, just a perfectly featureless sphere, it's a big cue ball, and you made a circle of radius little r measured along Earth's surface, and you found its circumference, how big would the circle need to be? What would little r need to be such that the difference between 2 pi capital R sine theta, 2 pi sine little r over big R, and 2 pi little r was 1 meter? How big a circle would you have to draw for that difference to be 1 meter? And then to your precision, you'd be able to tell, I'm living on a curved surface rather than a flat surface. And you know, we can do that sort of thing, and it turns out the flat earthers are wrong, which will never convince them of that. But it's really easy to show that we are living on a curved surface in many, many ways, of course. What questions do you have at this point? Yes?
I'm just like wondering, like, why exactly, why isn't there 2 pi r?
Where?
Like, why?
Oh, why did I drop the R? Because I forgot to include it. Thank you so much. Yes. Yeah. It belongs there. Absolutely belongs there. Yes. So sweet. 2 pi big R in little sign. Little R.
Would have said, had you not said?
Yeah. So that's what it's supposed to be. 2 pi capital R sine little r over big R, yeah, is what you will measure. But if you imagine yourself on a flat surface, you would expect it to be 2 pi times little r, and so that you get something less than 2 pi little r is telling you that you live on a curved surface. You deduce that you live on a sphere from that. By the way, when you're doing the problem, I'll add this to the problem statement hint. You'll want, because you're going to be taking the difference of these two terms, and so you're going to be taking the difference of things that are close to one another and trying to solve for little r, which has a sign in it, and it gets a little messy. You'll want to use, it's so hard to convince people of how useful Taylor series are and all this kind of stuff. Oh my God, so useful. You'll want to use the two-term, capital Taylor series approximation that sine theta is approximately, what are the first two terms in this Taylor series for sine theta? What's the first term? Sine theta for small theta is approximately, say it again, say it proud. Theta, approximately theta, what's the next term? Because not exactly theta, what's the next correction, so to speak? What's the Taylor series for sine theta? It's theta minus, no, it's not. That's in the cosine. But the sine, it's every other. The sine is an odd power series. The cosine is an even power series. So the next term is going to be what power of theta based on what I just said? 3 minus theta cubed over 3. 3 factorial. Yeah. You're going to want to use that two-term approximation. The next term is theta to the 5th over 5 factorial minus theta to the 7th over 7 factorial. But just use the first two terms, and you'll get a nice, easy to solve for expression for what little r should be based on that. If we're a cosine, it'd be 1 minus theta squared over 2 factorial. Plus theta to the 4th over 4 factorial, etc., etc. And remember, e to the x is 1 plus x squared over 2 factorial plus x cubed over 3 factorial, and so forth. So they're all kind of similar to one another, which shows up in the idea that e to the I theta is cos theta plus I sine theta. You can prove that, quote unquote, by plugging in I x into the Taylor series for e to the x. Anyway, on the 3-sphere, we have this additional polar angle chi, whatever you want to call it, which is angle away from, if you will, the w-axis in 4 dimensions that we're stacking our 2 spheres along. So with a 3-sphere, you've got a polar angle theta on each of the 2 spheres of which it is built, and a polar angle chi along the stacking, away from the stacking axis, that 4th direction, W, if you will, axis that you're stacking your 3 spheres, your 2 spheres along. And again, in the last homework set, you'll get to add yet another polar angle in order to come up with the metric on a 4-sphere as opposed to a 3-sphere. Because on a 4-sphere, you're stacking 3 spheres along yet another direction that's perpendicular to the 4 directions of 4-dimensional space, and you'll need another polar angle relative to that axis. You don't look excited enough about that. You're okay, cool. Okay. You're going to be so happy when you actually get to the problem. Okay. Questions, comments, observations? So we've introduced the metric on flat space and on spherical space. Let's write down the metric in hyperbolic, saddle-shaped space. So I'm going to write this as though it's the natural extension of what we've been writing, which means it's back in the notes from last time that this is the extension of. So it was flat, metric and flat space. Spherical, metric and spherical space. Oh, let's do all this cool stuff. And now, hyperbolic is the next one. That's the third possibility for the shape of space in an isotropic and homogeneous universe. Saddle-shaped, but of course, a three-dimensional saddle instead of a two-dimensional saddle, and it has to have constant negative curvature, which you can't embed. Even in 4 dimensions, you need 5 dimensions or more. And if we write down the metric, ds squared is c squared dt squared minus scale factor a of t squared times dr squared. So far it's looking just like it did for the flat and spherical cases, but now we're going to add plus r naught squared, and then instead of sine squared little r over big R naught, it's going to be sinh squared, hyperbolic sine squared of little r over R naught times d theta squared plus sine squared theta d phi squared. Need to close that parenthesis right there. So we've got sinh instead of sine. Anybody remember what's the definition of sinh x? Yeah.
Isn't it like e to the x minus e to the negative x over 2?
Yeah, sinh x by definition is e to the x minus e to the minus x over 2. Which is similar to sine theta, or sine x is e to the ix minus e to the minus ix over 2I. So this is related to that idea. In fact, the sinh of x is the sine of ix, as a matter of fact. If you plug in ix, you get into the formula for sine in terms of complex exponentials, you get sinh x. So sinh x is just defined to be that combination of those two exponential functions. Right, so if we collect them all together, just to put them all in the same place, you can directly see how they're related to one another. For flat space, for flat space, ds squared is c squared dt squared minus a of t squared times just an ordinary flat space metric that has this multiplication by the scale factor there. So for ordinary flat space, you've got dr squared plus what are the other two pieces? See if you remember, it's just the metric and spherical coordinates. Dr squared plus, so there's an r sine theta term in there. Let's do the d theta one first. So this direction one. This is the z-axis. What's that little arc right there? Go a little d theta at a distance r from the origin. R d theta, so we've got r squared, theta squared, d theta squared, and then we've got this one, right, where it's like, I go d phi, but it's a distance of r r sine theta times d phi. So we've got a piece that's r squared sine squared theta d phi squared. For spherical space, we've got c squared dt squared minus a of t squared. There's the scale factor, which says space is growing. Could be shrinking, but it's growing. Dr squared always stays the same there. Plus, and then we've got this business, capital R squared sine squared little r over big R times the other stuff, d theta squared plus sine squared theta d phi squared. This is supposed to be r naught because we have a radius of curvature when the scale factor is 1. So this is that polar angle coming in, again, in the fourth direction. And then we just wrote down the hyperbolic version. ds squared is c squared dt squared minus a of t squared, dr squared plus, and what am I going to do for that next piece? Instead of sine, I use, it's so easy, instead of sine I use, why it's so easy, it's a cinch, yeah, it's a cinch, it means it's easy here. So, plus r naught squared, cinch squared r over r naught, this same piece right here, d theta squared plus sine squared theta d phi squared. And what we're going to do, just to save writing, is we're going to call that combination d capital omega squared. Because now we're going to write the Robert, this is, so together, these are the, we're going to write these in a form that's the standard so-called Robertson-Walker metric. We use a different coordinate rather than little r. Because by using that coordinate, they all look essentially the same. Because of the way that coordinate is defined. So, questions, comments, observations? Just think in 4 dimensions and it'll be so obvious how, or, you know, just it'll be so obvious, it's just intuitive how all this works. But, well, with the hyperbolic one, you need to work in 5 dimensions, think in 5 dimensions in order to visualize the surface. Good luck with that. Even after my deal with Beelzebub, I'll still be like, if only everything in 5 dimensions. Hey, Beelzebub, I'll give up some more so I can think in 5 dimensions. Okay. So, often, a coordinate that we call just x, which is, by definition, capital R naught sine of little r over r naught, that thing that keeps showing up as multiplying the d omega squared term, is used as the co-moving coordinate to label each two-sphere. Instead of using little r, we're going to use little x. In other words, we're just making this definition. It's related to little r, but we're going to use little x instead. Often little x, that definition, is used as the co-moving coordinate, the one that doesn't change, that just follows spherical surfaces around and labels spherical surfaces. Remember, little r does not change. The grid is expanding with the universe, is used as the co-moving coordinate to label two spheres. Spherical surfaces, ordinary two-dimensional spherical surfaces in space, centered on us at the origin. Anybody can say they're the origin, so we're calling ourselves the origin. This is all written with respect to some arbitrarily chosen point in space to be the origin of coordinates. Then we have for spherical space, if the universe is spherical, we would have x is equal to, let's see, to label two spheres in spherical space, and I'm going to make a similar definition in hyperbolic space, but I'll just use the sinh instead of the sine. X is r naught times the sine of little r over r naught. If x is r naught sine of little r over r naught, what's dx? So I want to take a differential of both sides. Is r naught constant or does it change? R naught is the radius of curvature of the universe when the scale factor is 1. So does r naught change or not? It doesn't, because it's defined to be the radius of curvature of the universe at a particular time when the scale factor is 1. And we usually take that particular time to be when? When do we take the time to be when the scale factor is 1? Now. Yes, we say now. Okay? So r naught's a constant in there. How about little r? Well, that's not, because we're saying, well, what if I go to different values of little r? How much does x change if I change little r? So if if x is r naught sine little r over r naught, what's dx?
Cosine of r over sine.
R naught cosine little r over r naught times 1 over r naught, right? Because you have to differentiate inside function as well. So dx is r naught cosine of little r over r naught. All that times 1 over r naught, the derivative of the inside function. Well, the r naughts cancel, and you just get r naught cosine of little r over r naught. But wait a minute. Can we put that back in terms of sine of r over r naught? How can I write? Did I do something wrong? What's that? Yeah, because when I took this derivative for dx, it's r naught cosine little r over r naught times the derivative of the inner function, 1 over r naught. So those, yeah. I see what you mean, yeah. Thanks. Correct. Yes, thank you. Yes. Absolutely correct. Yes, thank you. Appreciate that. How can I write cosine of r over r naught in terms of sine of r over r naught? only there are relations between sine and cosine. Yes? Yeah, so right, so like, you know, how can I write this in terms of the sine of r over r naught?
Square root, I'd say 1 minus sine squared.
Exactly, it's the square root of 1 minus sine squared of r over r naught, because cosine squared plus sine squared is 1, right? So therefore, cosine is the square root of 1 minus sine squared. So I can say that this is the square root of 1 minus sine squared of r over r naught, using the fact that cosine squared r over r naught plus sine squared r over r naught is 1, because cosine squared is something plus sine squared of that something is always adding up to 1. But notice that sine of r over r naught is x over r naught from our definition of what x is. Sine of r over r naught is x divided by r naught. So therefore, I can write this as 1 minus x over r naught quantity squared. Oh, and what am I forgetting in my dx here? I'm tired. What am I forgetting in my dx here? I forgot one piece. I differentiated, so dx is blah, blah, blah. Can I only have a differential on one side? I need what over here? dr, I need the dr, absolutely. dr, 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 dr everywhere, dr is everywhere. No, because I just took dx here. Yeah, so dr is just sitting there. All right. So in spherical space, dx is square root of 1 minus x over r naught squared times dr. Now I'm going to do the same thing for hyperbolic space. Because what I'm going to want to do is write the metric where I have x everywhere instead of r. So this says dr is equal to dx over the square root of 1 minus x naught over r squared. So in my metric, instead of writing dr squared, I can write dx squared over 1 minus x naught squared over r naught squared. And not x naught, just x over r naught squared. So I'm changing variables, in other words. Questions at this point? Nope. Unhappy about something? Did I leave something out or something like that? Or you're just like, why am I doing this? Or, I mean, in the end, we're going to write the metric where it has dx in place of dr and x in place of r. And we'll see that when we do that, the metric for all three cases looks the same, except for what we're going to call kappa, the curvature constant. And the curvature constant will tell us which space we're in. It'll be 0 in flat space, +1 in spherical space, and -1 in hyperbolic space. Hyperbolic space, we're going to say x is r naught sinh, wow, I wrote h bar because you bar so many h's in physics. Sinh, it's like something, there's like, what did that say? What happened in my brain that did that? You know, but anyway, there's some circuit that got fired that shouldn't have. I'm always fascinated by that sort of thing. And that really meant something about my synaptic connectivity that I said H bar right there without even thinking about it. But anyway, R naught sinh R over R naught. So we want to do the same thing we did over here. We want to take dx, and does anybody know what the derivative of sinh is? It is in fact cosh, yeah, or cosh. I like to say cosh, but cosh makes sense too because it's cosine. But, so yeah, I'll say cosh because it's cosine, so cosh. It seems kosher. Yeah, there we go. So dx is going to be r naught cosh r over r naught times 1 over r naught times dr. I'm remembering dr this time. Sinh differentiates to cosh, as you can easily convince yourself, because cosh is e to the x plus e to the minus x over 2. So you can easily show yourself that sinh differentiates to cosh. Part of the reason we make the definitions is because you get those similarities like that. And now, all right, so this is going to be, I got room here, so I'll just keep going here. So it's just cosh r over r naught dr. But now I'm going to use the fact that there's this identity, which you can prove to yourself using the definitions of sinh and cosh, that cosh squared w minus sinh squared w is equal to 1. Instead of plus, it's minus with sinh and cosh. Cosh squared minus sinh squared is 1. So I can replace cosh with square root of 1 plus sinh squared. So this is the square root of 1 plus sinh squared r over r naught dr. But here in hyperbolic space, sinh r over r naught is x over r naught by our definition up here. So this is the square root of 1 plus x over r naught squared dr. Which says this time dr is dx over the square root of 1 plus x over r naught squared. Whereas in spherical space, it was dx over the square root of 1 minus x over r naught squared. So they're very similar, except there's a minus in this one and a plus in this one. Do you have a question?
In hyperbolic, is it not plus cosh squared plus sinh for the identity?
It is minus. This is the identity. It is a minus sign in the identity. So that this shows up as a plus. And you can prove that to yourself. You can just show it to yourself because cosh x by definition is e to the x plus e to the minus x over 2. And sinh x by definition is e to the x minus e to the minus x over 2. And just plug it in and you'll see that cosh squared minus sinh squared is 1. Maybe I should put w's there, but it doesn't matter what you call the argument of the function. So notice that if we say with the curvature constant, kappa, this is a kappa, not a k, that's a kappa, kappa equals 0 for flat space, plus 1 for spherical space, and minus 1 for hyperbolic space. Can I erase stuff on the board over on the right side here? Did you say yes or no, Kathy?
On that.
You're done, okay. Because you kind of went, I think you were kind of, oh yeah, I don't need it. And I was like, wait a minute, that's a no that you're shaking your head. Okay. Oh, anybody else? Can I erase this? I only care about Anushka and Kathleen, the rest of you. Okay. I'm just assuming you all were okay with that too. If we make that definition, then dr is dx over the square root of 1 minus kappa times x over r naught squared in all three cases. In all three cases, because if you're in flat space, dr is dx, because in flat space, r naught is essentially infinity. The radius of curvature of a flat universe is infinity, because it's not curved. And so x is just equal to r in that case. And in spherical space, if I define kappa to be plus 1 in spherical space, then the square root of 1 minus x over r naught squared is also 1 minus kappa times, square root of 1 minus kappa times x over r naught squared. If I make kappa plus 1 in spherical space, I can certainly insert a 1 right there. I haven't changed anything, so it's still the same thing. And if I'm in hyperbolic space, where dr is dx over 1 plus x over r naught quantity squared, well, that is also square root of 1 minus kappa x over r naught squared, where kappa is minus 1. Because minus minus would be plus 1. So this is in all three cases. And this is why it was decided to do this, because it always looks the same, and the only difference is whether kappa is 0, plus 1, or minus 1, and that tells you whether we're in flat space, spherical space, or hyperbolic space. Yes?
Like, so with like the thing where you could like go a certain amount of distance and then walk around and be like, it's this. How would that work with like hyperbolic space, like the saddle? Like,
Yeah,
would
so
it be the same thing?
it's the same sort of idea, yeah. So let me throw in here that if you look at the area of a two-sphere in any of these spaces, so let's radial coordinate dr when the scale factor is 1, so that its actual distance away from you as measured in space, how far you have to fly to get to that two-sphere. That's going to be, if you look at, organize myself here, if you look at any of these metrics, let me say this. All right, so we have PS squared is C squared dt squared minus A t squared, and then I'll stick in just the r coordinate for now instead of x, dr squared plus, and then I'll make it 1 or r naught sine little r over r naught, or r naught sinh little r over r naught, one of those three, depending which space you're in, times d theta squared plus sine squared theta d phi squared. That's the metric. To find that area of that sphere centered on the origin, a distance little r away from you, what am I going to set equal? What am I going to set to 0 in the metric? If I'm finding the area of the sphere, which two coordinates are changing and which two coordinates are staying fixed if I want to find the area of the sphere? Yes?
d theta and d phi.
D theta and d phi are changing. I'm going over the surface of the sphere. And dr and dt are 0 because I want the sphere all at one instant of time, so dt is 0. And I want dr to be 0 because I want to stay on the surface of that sphere. So to find the area of the sphere, set dt equals dr equals 0, so that I'm staying on the sphere at a single instant of cosmic time. And so the area of the sphere I'll get by integrating over theta and phi. And if I'm setting a of t to be 1, I'm saying let's do this at time when a is equal to 1, then a will be either 1 or r naught squared sine squared, oh these are all supposed to be squared, r naught squared sine squared r over r naught, or r naught squared sinh squared r over r naught times the integral over theta and phi of sine theta, what am I going to do? Sine theta d theta d phi, sine theta d theta d phi, because remember that the arc lengths are going to be r naught, if I'm in spherical space, for example, r naught sine little r over r naught times d theta in the theta direction, because this is like the radius of the sphere in the higher dimensional reality, if you like. And this thing times sine theta d phi in the other direction. So I integrate this to find the area of the sphere. And if I integrate over the surface of the sphere, phi goes from what to what?
0 to 5.
Phi is the azimuthal coordinate, 0 to 2 pi. And theta goes from what to what? 0 to pi. I assert that you know the value of that integral. 4 pi. It's always 4 pi, right? That's the integral over solid angle. And so what I get, I have to erase this, what I get from all of this is that the area of the sphere is 4 pi times one of these three things. It's either 4 pi times 1 times r naught squared sine squared r over r naught, or times r naught squared sinh squared r over R naught. Notice I can do the following. If we are in spherical space, then, sorry, over here, I made a mistake. This is supposed to be just R squared if we are in flat space.
I'm not understanding how's that written. Is that the whole term?
So hang on for a second. I didn't want to correct this. Yeah. So my stacks were supposed to have little r squared on the top instead of 1 for flat space. Okay. So now you're saying there's something you don't understand, which is what?
What's the stack? Why?
Right. So what I mean by this is pick one depending on what kind of space you're in. If you're in flat space, the answer is this times all of this. If you're in spherical space, it's this times all of this. If you're in hyperbolic space, it's this times all of this. So this is saying, and this is supposed to be an r squared right here, this is saying in flat space, the area of a sphere is 4 pi little r squared. In spherical space, the area of a sphere of coordinate little r at time when the scale factor is 1 is 4 pi r naught squared sine squared little r over r naught. And if you're in hyperbolic space, it's 4 pi r naught squared sinh squared little r over r naught. In those cases.
Would that one up there be r squared?
It would in fact be r squared, thank you. I was like, where's the other one? Because I'm like, ah! Okay. This would in fact be r squared up there. Yes, that's r squared. Yes?
In the very top right is where it's sine squared d theta squared.
Yeah, it's sine. Oh, God. This is not a good day. God. Okay. Thank you. I'm just testing y'all, and you are passing with flying colors. Big thumbs up. Sine squared theta d friggin' phi squared is what that's supposed to be, yes. Okay. Yeah. And meanwhile, notice, if I'm in spherical space, what variable did we say we were going to make this? That's x squared, right? If we're in hyperbolic space, what variable is this? X squared. And if we're in flat space, what variable is this? Still x squared. Because in flat space, x is r, because r naught's infinity. In flat space, there's no curvature, so the radius of the sphere is infinity in flat space, so to speak. So in every single case, the area of a sphere is 4 pi x squared. In every case, the area of a sphere is 4 pi x squared. So in other words, the interpretation of this variable x is it's the thing that makes the area of a sphere that you draw 4 pi x squared. If I want to find what x is on any sphere surrounding me, I have my anti-minions go measure the area of that sphere, and once they report it to me, I say, I'm going to say that 4 pi x squared is the area of that sphere, so therefore x is the square root of the area of that sphere as reported by my anti-minions divided by 4 pi. Square root of area over 4 pi, that quantity is x for every surface, every sphere surrounding me in space. And if I insist on using little r instead, well then I have to use these more complicated formulas to give me the area of the sphere. If I already knew the radius of curvature of my space, which I figure out by measuring various things, I could plug in these formulas. But it's convenient to have this coordinate x, which is already built in that the area of the sphere is 4 pi x squared, and furthermore, the circumference of a circle is just 2 pi x. So if I have a circle drawn around me, and my anti-minions measure the circumference of the circle with their anti-roller tape, and they give it back to me, I'll say, aha, the value of x on that circle is the circumference divided by 2 pi. It's true in no matter what shape of space I'm in. That's what x means. And I think that answered your question. I don't remember your question anymore.
I think that makes sense.
But I think it was like, something like that. So, all right. Again, this is the the kind of thing that you got to go home and think about this in your spare time, or come talk to me about it. I love talking about this. It's not the sort of thing that you can fully digest, I think, when I'm just presenting it to you. It is the kind of thing you need to think about for a while. You need to, some of you will know what I mean, you need to detraxelinate it in order to understand completely what it means. Okay, let's take a break, shall we? Wow. Wow, well that was a fun little story time. I enjoyed that actually, yes. And I'm feeling a little bit better about my childhood. All right, so.
Collectively crazy.
Yeah. I mean, I think it's good though, in the end, right? I mean, you know, my wife will do weird things and I'll be like, wow, you're weird. And her retort is, if I weren't, your life would be, right? And so I think it's kind of true, right? So good, right? You want your life to not be. So, well done, well done. All right then. So after all that, let's collect these results together, throw them into a blender, and what comes out? Yes, fire, right? Putting all this together in a blender with some rust and aluminum. That's going to make perfect sense to the audience at home. Oh, and a tire. Need a tire too, because we're going to need the circumference of that tire. So,
Poor audience at home.
what's that?
Poor audience at home.
Yeah, poor audience at home, that's right. You know, if you show up for class, you can have this kind of fun too. Just saying. We can write ds squared is equal to c squared dt squared minus a of t squared times, so our dr squared becomes dx squared over 1 minus kappa times x squared over r naught squared. So that's the piece we developed from dr and dx, that relationship, plus x squared d omega squared, where d omega squared is just our notation to save time, d theta squared plus sine squared theta dt squared, where kappa is either plus 1 for spherical space, it's 0 for flat space, and it's minus 1 for hyperbolic space. And this is what we call the Robertson-Walker metric. It tells us space-time intervals in a homogeneous isotropic universe. And I'll throw in, we've said it, but let's make it explicit here, that what does x mean? What's the circumference of a circle in terms of x? The circumference is 2 pi x. Yep, just 2 pi x, right. And what's the area of the sphere in terms of x?
Square.
Yeah, 4 pi x squared. Yeah, 4 pi x squared. So if I want to know what x is, I have my anti-minion. I consider a sphere centered on me at the origin. So relative to the origin, my anti-minions go measure the area of that sphere, and 4 pi x squared is that area. Or I draw a circle, and my anti-minions walk around and measure its circumference, and 2 pi x is the circumference. So circumference over 2 pi is x. So I could actually assign, in principle, figure out what x was at various locations. And theta and phi are just, well, I draw a z-axis, and theta and phi are the usual things. Yes? Of course it is. Of course it is, yes. You too are passing this test. Yep. Just checking on y'all, just being sure you're paying attention here. Yep. That's what you do when you're a good teacher, is you put little bombs in there, see if they notice them, right? Yes. Okay. God. Okay, so there we are. All right. You know what? After all that, turns out we're pretty convinced the universe is essentially flat. It's the most boring case, that the universe is just flat. Back when I was a kid, that wasn't so widely realized. And so there was a lot of effort in trying to measure whether space was flat, spherical, or hyperbolic. But it turns out there's good reason to think that space is flat. Because it turns out that if the universe was even slightly curved early on, then it would become more and more curved after that. And so for the universe to be anywhere close to flat today, it would have to be unbelievably close to flat soon after the Big Bang. So I hope to get to that later. But in the end, just know that, gosh, the universe appears to be flat. And if you took cosmology or you read about this sort of thing, you'll know that it's because inflation would flatten the universe. A period of inflation early on would take a universe that wasn't flat and make our region of it virtually flat. Basically, it implies that the part of the universe we can see is a tiny, tiny part of a much larger reality. And just as the surface of the Earth looks flat to us because its radius of curvature is so large compared to the area that we can see, the universe as a whole might be this curved mess, but the part of it that we can see is so small compared to the universe as a whole that our part of it, for all intents and purposes, looks flat. Even though on the big picture, it may not be. So, any questions before we continue? Which I do kind of, I want to be like in a cool spherical universe where it's like we're living in curved space-time as in the universe as a whole. Oh well, too bad. The equations are simpler for flat space, so there's that. All right. Proper distance. You've mentioned this. I'm going to remind you. Here's you. And you are at the origin, 0, 0, 0. So it's really all of us. But it'll be you. There you are, you're smiling. Why are you smiling? Because you are thinking about astronomy 311 right now. And meanwhile, there's this galaxy off in the distant universe. We've got a beautiful spiral galaxy right there. Oh, glorious. Oh, it's so beautiful. And it is at our theta phi. And we said before that its proper distance at time t you get by integrating A of t dr at fixed time t. Because we want to know how far away it is now. So you integrate, the element proper distance is a dr, so you integrate that for fixed time t, so the scale factor at any given moment can be pulled out of the integral. So maybe this was a billion years ago, and this is Florbaflob on Zorkon thinking about instead of you, but if it's today, it's you thinking about Strine 311. And so you just get A of t times r. Right? This goes with the idea that r is distance away from this at the time when the scale factor is 1, and at other times when the scale factor has some different value, where you have to multiply it by the scale factor. But if the galaxy has no peculiar velocity, if it's always just being carried along by the expansion of the universe, then little r is fixed. It's the fixed moving coordinate. And so at any time t, its proper distance from us is A of t times r. When was A of t 0? Why, that would be at the Big Bang. Yeah, that'd be at the Big Bang, right? And A of t's been increasing ever since then. And what's A of t today? It's 1. Why is it 1 today? Why not some other time? Because it's now for us, right? So you just make it 1 at our time. Yes?
Is A of t like linear? Like is it?
No, see, that's the thing. It depends on the composition of the universe, what A is as a function of time. You need a model of the universe to know what A would be as a function of time. Alternatively, observations give you insight into what A was as a function of time, and that gives us insight into how much dark matter is there, how much baryonic matter is there, how much dark energy is there. That's all tied together. So that's a great question. And the idea with inflation would be there was an early time when A was increasing exponentially, super exponentially, very, very, very rapidly early on. And then when inflation stops, A stops increasing that quickly. It increases more gradually. Okay, so writing out what I was just saying, as the universe expands, as the universe expands, r stays constant, if the galaxy has no peculiar velocity. And remember, here peculiar doesn't mean strange, it means unique to it in this case. It's its own particular peculiar velocity relative to the expansion. If it's just being carried along by the expansion, in a sense you can kind of think of it as, even though motion is relative, but if basically the idea would be, at any given point, you can say, is the cosmic microwave background, we haven't talked about that, but you might have heard, if the cosmic microwave background is isotropic at your location, you have no peculiar velocity relative to the expansion of the universe as a whole. The Milky Way, we actually see the cosmic microwave background is hotter in one direction and cooler in the other. So we have a peculiar velocity with respect to the expansion of the universe as a whole. But if we ignore all that, r stays constant while A increases, because the universe is expanding. So let's look at the recession speed. How fast is the galaxy getting further away from us? The galaxy's recession speed, how fast the distance to it from us is increasing because of the expansion of space, is what's called V equals VP, we'll call it like this. current proper velocity, if you like, is dp dot, the time derivative of dp, time derivative of the proper distance. Okay, but dp is a of t r is a constant, so dp dot is what? I did some of this earlier, but we're going to extend it now. Product rule would say normally it would be a dot r plus a r dot. What's r dot equal to? Nothing, because r is constant. R follows the galaxy, right? It's a co-moving coordinate. It stays fixed. R expands as the universe expands. So R labels where the galaxy, how far away the galaxy was when A is 1, and it just, the whole grid is like graph paper that stretches with the universe. So this is just A dot times R. But that's A dot divided by A times AR. In other words, just multiplying divided by A. So it's A dot over A times, what was A times R again? What was A times R? What's A times R equal to? dP! dP! It's A dot over A times dP. So this says the speed the galaxy is getting away from us at, the rate of change of its distance from us, is whatever A dot over A is at time t times how far away it is. In other words, the recession speed is proportional to how far away the galaxy is. If only there was a law named after some famous astronomer that said that recession speed is proportional to distance. Is there a law named after some famous astronomer that says how fast the galaxy is moving away from us is some number times how far away the galaxy is from us? Who's that famous astronomer? It is Hubble. It's Hubble Bubble. Yes. Oh, I call it Hubble Bubble because it rhymes, I guess. It's Hubble. So in other words, what we've learned here is that the galaxy's velocity is A dot over A times its proper distance, its distance now from us. So Vp as a function of time is equal to, why, let's call that h of t times its proper distance as a function of time, where h of t is A dot over A at time t, derivative of A, derivative of the scale factor with respect to time, over the scale factor itself, is the Hubble parameter. We've mentioned it before, and here's how it's related to the scale factor and its time derivative. It's the Hubble parameter. Right, so we meant that before when we were talking about the expansion of the universe. We said V is HD, or H, the Hubble parameter, can vary with time. At different ages of the universe, the relation between distance and recession speed can change with time. And now we know, oh, well, in terms of the scale factor, it's its time derivative divided by the scale factor at any given time. Let's evaluate this now. Evaluate it at the present time. Why, we would get that Vp at time t naught is, well, let's call that h naught times proper distance now, where h naught, which by definition is h evaluated at time t naught, is equal to a dot over a evaluated at time t equals t naught, is the Hubble, I don't say parameter this time, instead of parameter I say it's the Hubble constant, because the Hubble constant is the Hubble parameters value today. That's what we mean by that. It's the Hubble constant, which is just the Hubble parameter now. Notice if we do decide, we don't have to, but if we do decide that A is 1 today, then this just becomes A dot today. What are the units of A dot? So we say that distance is A times R. Distance has what units? Like any self-respecting distance, give me a distance unit. Give me a distance unit! Give me a distance unit!
Meters?
Meters! Or light years, or parsecs, or whatever you want it to be. What units does R have? It's the radial coordinate, or the common coordinate is the proper distance now. So what are the units of R? Meters also. R is also meters. So what are the units of A?
Dimensionless?
Dimensionless. A is dimensionless, right? Because it's just the thing you multiply this distance thing you would by to get the actual distance, right? So A is dimensionless. So what are the units of A dot? A dot is the derivative of A with respect to t.
1 over.
Yeah, 1 over seconds, right. So A dot has units of inverse seconds. A dot over A has units of also inverse seconds, right? Because A is dimensionless, right? So A dot has units of inverse seconds. Just in general, A dot has units of inverse seconds, and A has units of nothing. So A dot over A has units of inverse seconds. So in other words, the Hubble parameter has units of inverse seconds. Right? That's worth pointing out. H has units of inverse seconds. H has units of time units to the minus 1. I'll just put it that way. E.g. seconds to the minus 1 if you like. In a coasting universe, we call it. It's not the one we live in, but in a coasting universe, all galaxies have a constant recession speed from us. So they're all just moving away at a constant speed. However fast it's moving away now, it's always been moving that fast away from us. It's not the real universe, but take that as the first approximation. So here's this galaxy. Let's say we're doing this today. This will work whenever we do this. It's today. There's this galaxy, the distance d from us. It's moving away from us at speed v. Run the clock backwards. Right, let's reverse time. Still a distance d away, but what do I do with v now? It's moving towards us instead of away from us. In other words, I'm saying let's reverse. Universe has been expanding. Let's run the clock backwards and ask ourselves, how long until everything's on top of us? A galaxy half as far away, what's true about its recession speed? If it's half as far away, I'll even draw one here, right? So here's this other galaxy, half as far away, that's d over 2 away. What's its recession speed compared to v? Hubble law. Yeah, right? What's the Hubble law say? V equals V and D are related how according to Hubble? Expansion of the universe. V is HD, right? V is HD. Today it's H naught. At other times it's some other value. And I'm not saying here that H naught is constant. I'm saying the velocity stayed constant. H is actually changing here. Because if this velocity of this galaxy stays the same, when the scale factor is 2, it's twice as far away, but it's still moving the same speed. So therefore, the Hubble constant is only half as big because it's twice as far away, but still moving the same speed. So the Hubble constant would be diminishing with time here. The Hubble parameter would be diminishing with time in this scenario. But I just want to know, okay, I'm assuming that whatever h is today, v is hd, describes how fast a galaxy is moving away from us. Okay, so it's moving back towards us at what speed? If I run the clock backwards, it's distance d away, how fast is it moving towards us? In terms of h and the distance. HD, I'm not trying to make a tricky question here. HD, okay. And I guess I will say, okay, I'm doing this today so I can say v is h naught d, but now I'm going to assume that it always is flying back towards us at the same values it is today. So the Hubble parameter will be changing, but the velocity is always h naught d based on what the Hubble parameter is equal to today, the Hubble constant today. Okay, here's my question. How long ago was the Big Bang? How long ago was the Big Bang? In other words, how long ago was that galaxy on top of us? And this galaxy half as far away, it's only moving at speed v over 2, will also be on top of us at the same moment because it has half as much distance to cover at half the speed. So if I run the expansion backwards, everything lands on top of everything else at exactly the same moment. Because something twice as far away is moving twice as fast, something 3 times as far away is moving 3 times as fast. So if I run that backwards, everything smacks into me at exactly the same moment. Okay? So how long ago was the Big Bang? If that galaxy is, when I run the clock backwards, approaching me at speed v equals h naught d, traveling the distance d, how long ago was the Big Bang? In other words, if something's driving towards you at a certain speed and it has to cover a certain distance, how long does that take? Kinematics. Yeah, what's the relation? Kinematics says, right, x equals x naught plus
AT.
yes, thank you. VT, right? Yeah. Or, in other words, x minus x naught is VT, d is VT, right? So T is d over V, right? D over V. Why? How long's that galaxy been flying away from us? Flip it around. How long till it's back on top of us? I run the clock backwards. Why, it's d over V. But d is equal, v is equal to h naught d. Can anybody simplify that expression for me? 1 over h naught. 1 over h naught. In other words, the age of the universe, if galaxy recession speeds stay constant, is t equals 1 over h naught inverse. So by measuring the expansion rate of the universe, we get an estimated, we estimate its age. Now, the real universe isn't coasting, so this isn't right. You need to know the details of the expansion history to get the actual age. But it turns out, given the expansion history of the universe, if you throw out inflation, if you get rid of that little piece of it, which happens for such a short time it doesn't really matter, it turns out that h naught inverse gives you almost exactly, kind of by coincidence, the right age for our universe, even though it isn't really coasting. Even though galaxies are moving faster and faster away from us. The expansion of the universe is accelerating. It used to be we would be slowing down. Now the observations say it's accelerating. So you can estimate the age of the universe from the Hubble parameter. Now, the h naught is given in terms of funny units because we say it's like roughly 68 kilometers per second. I'm just going to say 70 because there's two different estimates based on hot spots and cold spots on the cosmic microwave background and based on local observations of galaxy recession speeds, and they are more than their standard deviations away from one another. That's called the crisis in cosmology. We have two different answers. And everybody's like, oh my God, we have a crisis in cosmology. When I was a kid, we were like, well, we think h naught is somewhere between 50 and 100 kilometers per second per megaparsec. We knew it to a factor of 2. So now it's like, oh my God, there's a crisis. There's the, well, the signals are so, it's like, oh my God, these days we're living in. But anyway, still, now that we know better, it is a genuine crisis. In that it's saying, there's something we're not understanding. h naught is 70 kilometers per second per megaparsec. Ultimately, does that have inverse second units? Are kilometers and megaparsecs, could you make those cancel in the end? Yeah, because megaparsecs is just a certain number of meters, right? So in the end, you could convert this into a number that was in inverse seconds, and we take its reciprocal, you just happen to get about 14 billion years is the answer for that. It gives you just about the right number. So understand that the Hubble constant, its reciprocal is a quick and dirty estimate of the age of the universe. Question?
When you say the coasting universe, all galaxies have a constant recession speed, that's like for each galaxy is constant, not...
Yeah.
Okay.
Yeah. So I better, yes, that's a very important clarification. And so once again, you've passed the test that I'm, leaving these little subtle things there to be sure you're paying attention. I am just so clever, aren't I? So yeah, all individual galaxies have a constant recession speed from us. Different galaxies have different recession speeds, but the individual galaxies all have a constant recession speed from us. And again, that isn't true. For the longest time, we tried to determine what's called the deceleration parameter because we assumed that the expansion of the universe should be such that any individual galaxy is moving away from us slower and slower over time. And the question was, well, what's the limit of that as t goes to infinity? Does it stop and come back? Does it fly away forever? Does it stop after infinite time? We kind of hinted at that earlier. But then, in the late 1990s, two independent teams observed type 1a supernovae in galaxies billions of light years away, and they both came to the same surprising conclusion: individual galaxies are moving away from us faster and faster instead of slower and slower. We don't live in a coasting universe. We don't live in a decelerating universe. We live in an accelerating universe. Galaxies are moving away from us faster and faster. But it turns out, and here's a kind of a quick and dirty on why we get about the right number here. So, and again, if you took cosmology, you've heard this before, and I'll remind you, and if you haven't taken cosmology, well, there. The universe is now dominated by dark energy, which provides a sort of anti-gravity that makes the universe expand faster and faster. But that only took over about when the universe was about 9 billion years old, right around the time the sun was being born. Before that, the universe was matter-dominated as opposed to dark energy-dominated. And in a matter-dominated universe, the expansion does slow down, and individual galaxies slow down over time. So what has happened over cosmic history is first galaxies were slowing down, and then since the universe was 9 billion years old, they've been speeding up, and those two effects just about balance out so that you get the right number from assuming that they've always been moving the same speed away from us, just by kind of coincidence. So that it works out nicely. Questions, comments, observations? Yes?
Just to confirm, so the ghosting universe is the one that's not accelerating.
So in a coasting universe, yeah, any given galaxy is moving away from us at a constant rate. You assume that it's always been moving away from us since the Big Bang at the same rate. But there weren't any galaxies right after the Big Bang. Shut up. No, just any given portion of the universe is moving away from us at the same speed at all times. That's the coasting universe. It's not the universe we live in. We live in a universe where any given point first was slowing down and then started speeding up 9 billion, at when the universe was 9 billion years old. So like about 5 billion years, almost 5 billion years ago, right around the time of the sun's birth. Just by coincidence, the universe was switching from matter-dominated to dark energy-dominated. Yeah, and it's been dark energy-dominated ever since, and dark energy really is a cosmological constant. It'll be more and more dark energy-dominated because a cosmological constant would have a constant density, whereas matter and radiation become less dense over time as the universe expands because photons and particles spread apart from one another. Whereas dark energy would be an energy associated with free space itself, if it's a cosmological constant, such that every cubic meter has the same amount of dark energy in it. And as the universe expands, you're making more space, and every bit of that space has dark energy in it. Where is it coming from? Nowhere! It's not coming from anywhere. It's just being generated from nothing. Because, does the universe conserve energy? No, it does not. Energy conservation for the universe as a whole is not a thing. As the universe expands, what happens to the wavelengths of photons? They get longer, right? They're stretched. What's that mean for their energies? Getting smaller and smaller. Where is that energy going? We mentioned it before. Nowhere. It's just disappearing. But at the same time, dark energy is, apparently, if it's right, if it's a cosmological constant, just being generated out of nowhere. Every time we make more space, so to speak, we get free dark energy coming along with it. Energy conservation is a local thing. It's not a property of the universe as a whole, because when you took mechanics, you may have learned that there's this fundamental relation that the total time derivative of the Hamiltonian is equal to its partial time derivative. So that if the Hamiltonian has no explicit time dependence, if we have time reversal invariance, if it's independent of time, then the total derivative of the Hamiltonian, the rate of change with time is 0, but the Hamiltonian generally represents the energy of the system. And so if the Hamiltonian of the system is no explicit time dependence, energy is conserved, but the universe as a whole is genuinely changing. The Hamiltonian of the universe is different now than it was around the time of the Big Bang, and it'll be different in the future. So the Hamiltonian has explicit time dependence, which means that the energy of the universe has explicit time dependence. Energy is not conserved for the universe as a whole. So there, let that sink in. Too bad the people at home have no idea what that means either.